Okay, thanks for coming to this discussion section. Firstly, we will work on problems related to sets and set proofs. Then we will go over 3 hardest problems from quiz 2. So let's get started. This is the first problem, the element-wise proof to prove the 2 sets are equal. I will give you 2 minutes to think about it, and then we will try to solve it together.
It looks like there might be an issue with the screen share. I don't quite.
Sorry?
It looks like it was the one that Faye was sharing.
Yeah. What's happened?
Oh, I just see problem 3 from quiz 2, and then the writing that Faye was doing.
Faye, can I move him out?
Oh, there it goes.
So if we want to prove 2 sets are equal, so we need to prove they are a subset of each other. So for this problem, we need to prove 2 parts. Part 1, we need to show A complement union B is a subset of universal set. And in part 2, we need to show the universal set is a subset of A complement union B. So James, can you see my screen? I write something on that.
Yeah, it's working now.
Okay, then we'll continue. So for each part, we can use element-wise proof. That means we need to choose an element from left-hand side. So we can let X is an element of A complement union B. And then we have X is an element of universal set. This is by the definition of union set or universal set. So A complement union B is a subset of the universal set. So we are done with the first part. In the second part, we still need to choose an element from the left-hand side. So we can let X is an element of universal set, and we need to prove this element is also a subset, or is also an element of A complement union B. In this one, we can divide it into 2 cases. Actually, we can, because X is a element from the universal set, then X is an element of A, or X is an element of A complement. This is by the definition of complement. Any question about this? Oh, okay. There's a question from Peter. Need to show contains A and A prime. Sure. Yes, this is what I'm just doing, or what I'm just doing now. So we can choose an element from A or A complement, and then to show in each case that it is belongs to A complement union B. So we can divide it to two cases. Let me use another page. So now we have two cases. Case 1, X is an element of A. And case 2, X is an element of A complement. And finally, we need to prove in both cases X is an element of A complement union B. So we started with the first case. When X is an element of A, then X is an element of, I think it's A intersect B. This has given from the problem. So we say by A intersect B is equal to A. And then X is an element of B. This is by the definition of intersection. And then X is an element of union B. This is by the definition of union. So we prove in the first case that if X is an element of A, then X is an element of A complement union B. But we still prove, but if we want to prove that the universal set is a subset of A complement union B, we still need to prove the second case. So when X is an element of A complement, then X is an element of A complement union B. This is by the definition of union. Thus, in both case 1 and 2, we have X is an element of, so universal set is a subset of A complement union B. And we still need to make a final conclusion. From part 1 and part 2, since A complement union B is a subset of U, a universal set, and universal set is subset of A complement union B, thus complement union B is equal. So we are done with the first proof. Any question about the first problem? Okay, let's go to the second one. we needed to use the contradiction proof to prove that the intersection of these two sets is empty. I will give you 2 minutes to think about it, and then we will work on it together. And here is a hint. So the original statement is that the intersection of these two sets is empty. So the contradiction should be it is not empty. Then please work on it for 2 minutes. Then we will discuss it together. So by contradiction, the contradiction is that the intersection of these two sets is not empty. So by contradiction, there exists an element X that is an element of the intersection of these two sets. And this means X is equal to 2k plus 1, and X is equal to 4L, where K and L are natural number. Okay, here is a comment. Assume not empty, then has an element X such that X is equal to 2k plus 1 and X is equal to 4m. Yeah, correct. Peter has already given us the pipeline he used to solve this problem. That's a great comment, and it is correct. And then I will use another method to prove it. So we have in this one, because X is equal to 2k plus 1, and it is also equal to 2L, then we have 2k plus 1 equal to 4L. And from the left-hand side, 2k plus 1 is an odd number, odd integer. This is by the definition of odd number. odd integer. From the right-hand side, we have full L. It is equal to 2 times 2m. Two times 2L. It is equal to 2m. This is m, where m is equal to 2L by the closure property of integer. So 4L is an even integer. And because left-hand side is equal to right-hand side means there is an odd integer and it is also an even integer. And this is a contradiction. Also, you can also prove by contradiction as shown by Peter. It is also right. So this is another method, and we still need to write down the conclusion. A plus 1. Oh, not integer. Natural number. Is empty. So we are done with this problem. Any question about this problem? Okay, let's go to the third one. Still, we need to prove two sets are equal and it is related to the power set. Still, we will firstly use 2 minutes to think about it, and then we will work on it together. Okay, in order to prove that this 2 set is equal, we still need to divide it into 2 parts. Part 1. Show the power set of A intersects the power set of B is a subset of power set of A intersects B. Still, we choose an element from the left-hand side. Let X is an element of power set of A intersect power set of B. Then we have X is a power set of element of power set of A, and X is an element of power set of B. This is by definition of intersection. Then X is a subset of A, and X is a subset of B. This is by the definition of power set. Any question about this sentence? Okay, then X is a subset of A intersect B. This is by the definition of intersection. So X is an element of power set of A intersect B. This is by the definition of power set. Okay, we choose an element from left-hand side and prove that this element is also belongs to the right-hand side. So we conclude that P power set of A intersect power set of B is a subset of power set of A intersect B. Now we're done with the first part. Then let's go to the next part. Power set of A intersect B is a okay. We need to show it. We haven't got this statement, so we need to show power set of A intersect B is a subset of power set of A intersect power set of B. So we still choose an element from power set of A intersect B. Then X is a subset of A union intersect B. This is by the definition of power set. Then X is a subset of A, and X is a subset of B. This is by the definition of intersection. Then X is an element of power set of A, and X is an element of power set of B. This is by the definition of power set. Then X is an element of power set A intersects power set of B. This is by the definition of intersection. So we prove that if we choose an element from the left-hand side, then it is also an element from the right-hand side. So the power set of A intersect B is a subset of power set of A intersect power set of B. Now we're done with the second part. Still, we need to write a final conclusion. From part 1 and part 2, since power set of A intersect power set of B is a subset of power set of A intersect B, and the power set of A intersect B is also a subset of P power set of A intersect power set of B. Therefore, these two are equal. Okay, we are done with this problem. Any questions so far? Great, let's go to the next question. Use the following, use the rules of, I think this is the rules for the logic to prove the Boolean algebra. Let's record that the rules of logic and for the set theory and for the Boolean algebra are the same. So all of them has three operators. For the logic, we have and, or, and not. For the set, it is intersection, union, and complement. For the Boolean algebra, it is and, or, and not. We still have two special cases. For the logic, we have contradiction and tautology. And for the set, it is the empty set and the universal set. For the Boolean algebra, it is 0 and 1. So although they have different representations, but the rules are the same. So we can use this, although this form is from the logic, we can still use it in the Boolean algebra, but make sure we should use different operators to represent it. Let's use 2 minutes to think about it, and then we'll solve it together. let's start it with the left-hand side. The left-hand side is A or B and B or C. So it is quite similar with the distributive formula. We can denote the first one as a single item and then implement the distributive formula. So it is equal to A or B and B or A or B and C. And because the priority of AND is higher than the OR, so we don't need to have to put the braces like that. So this is by the distributive. And then we can continue to use distributive, but we need to change the order of the first item and the second item. So it is equal to, oh, sorry, B. This is by commutative. We can use the distributive from this step, but if we take a close look at this one, we will find we have 2B in this item. So we can use the absorption, but we still need to change the order of A and B. So it is equal to B and B or A, or C and A or B. Then we can use the absorption to get the left, this item is equal to B. Oh, no space now. Then we can use the distributive for the second item. So it is equal to B plus CA or CB. This is by then these two items also these two items both has B. We can use commutative to change the order of it. B, C. Okay, we change the order of BC as well because we want to use this one. So it is equal to B plus C. A. This is by the absorption. Okay, I think I'm done. Okay, we still need to use the commutative to make it as the same format with the problem. So it is A, C, or B. Okay, we are done with this problem. Okay, there's some question about this problem. To move around value with C. Oh yes, I have a question from Elizabeth. That is, can you use the commutative property to move around value within a pharmacist? Yes, we can. See, so that we could reverse the. Yeah, yeah, you can. We have different ways to solve the problem, but please make sure that you use the format that exactly the same with the equivalence table. And if you can get the final answers, then we will accept, the TA will accept this answer. Okay, let's go to the next problem. From this problem, we choose the 3 hardest problem from quiz 2, and this is because the students want the solutions of quiz 2. So every time we finish a quiz, we will select several hardest problems from quiz 2 and discuss it in the discussion section. So I think all of you has already familiar with this problem, so we will start it directly. For this problem, we need to prove it by cases. So from the division theorem, given any integer n, we can write it as, we can have a k that is also an integer, that n is equal to 3k plus r. And well, r is the remainder, and it can be equal to 0, 1, and 2. So we have we have 3 cases. In case 1, r is the remainder is equal to 0, then n is equal to 3k. So in this case, n cubed minus n is equal to 3k cubed minus 3k. It is equal to minus, and it is equal to 3n, where n is equal to 9k cubed. This is by the closure property of integer. So in this case, n is divided by n cubed minus n is divided by 3. We still have the 2 cases. In the second case, r is equal to 1, then n is equal to 3k plus 1. Then n cubed minus n is equal to 3k plus 1 cubed minus 3k. Okay, then we need to place some algebra. It is equal to k2 plus 2k. Then we still need to show that this is divided by 3. So it is equal to 3 9k cubed plus 9k squared plus 2k. It is equal to 3m, where m is equal to so in this case, n cubed minus n is divided by 3. Then let's go to case 3. In case 3, r is equal to 2 and n is equal to 2k plus 2. So it is the thing that we need to use 3k plus 2 to substitute the n. And it is equal to 27k cubed plus 54k squared plus 33k plus 6. Okay, there's a question from Peter that split. I think you can use any mathematical algebra to do that. Either you can unfold it into items plus item, or you can unfold it to the item times item plus something like that. I believe Peter's answer is also right. So in this one, we still can use the m to represent that. Okay, m is an integer by the closure property of integer. So in case 3, n cubed minus n is divided by 3. So for all cases, we prove. No problem. You can interrupt me anytime you want. Okay. So we still need to write the final conclusion that for all cases we prove that n cubed minus n is divided by 3 for all n is an integer. So this is the proof for this question. Okay, let's go to the next question. This is the problem 6b from quiz 2, and we need to prove it by induction. So firstly, we need to have the problem statement. We need to prove the left-hand side is equal to the right-hand side. We use an to represent the left-hand side. And I use bn to represent the right-hand side. The problem the problem statement is the left-hand side is equal to right-hand side, that is AN is equal to BN. Then we needed to prove the base case. The base case starts from N equal to 1. So we needed to show P1. In P1, we have A1 is equal to 1 times 2 is equal to 2. B1 is equal to 3. 1 times 1 times 3 over 3, it is equal to 2. So we have P1, A1 is equal to B1 is 2. Then we need to make a hypothesis. Then inductive hypothesis. We assume Pn is 2. That means An is equal to Bn. Then we go to the inductive steps. We want to prove Pn plus 1 is 2, assuming Pn is 2. So we can start from Pn plus 1. It is equal to 1 times 2 plus 2 times 3 times 2, I think it's N plus, here. It's N minus 1 times N plus 1 because it is N plus 1, so we still need to add an additional item. So this is by the definition of An, and then here it is equal to An plus N plus 1 times N plus 2. This is by the definition of An. And then it is equal to Bn. This is by the inductive hypothesis. Then we use a function to substitute the Bn. It is equal to it is equal, because we have the 3 below, so we can add 3 to up, both up and the bottom for the second item. Then it is equal to and this one is equal to Bn plus 1. Now we have proved that, okay, I don't think I have an additional blank page. Then we will say that we have proved An plus 1 is equal to Bn plus 1 when we assume Pn is true. So we have proved the original statement is true. Okay, let's go to the next question very fast. Still, we can use the inductive proof for this problem. This problem is 6a. So, problem statement. We let the right-hand side Bn is equal to 3n minus 1. The statement is Pn is An is equal to Bn for our n is larger or equal to 1. Then we need to prove the base case. A1 is equal to 2. This is given in the problem. And B1 is equal to 3 to the power of 1 minus 1, it is equal to 2. So P1 is 2. Inductive hypothesis. We assume Pn is 2. So An is equal to Bn. Then inductive step. Show Pn plus 1, assuming Pn is 2. So for An is equal to 3, An plus 2, this is by the definition of An. Then it is equal to 3, Bn plus 2, this is by the inductive hypothesis. And then it is equal to, it's equal to 3 minus, I think it's this one. Double check. Okay, it's right. Then it is equal to 3 plus 2, it is equal to and this is equal to Bn plus 1. So Bn plus 1 is true when Pn is 2. So we finish this proof. Sorry for running out of time. If you have any question about the quiz 2, please go to our TA office hour. So any other question before we wrap up? If no, then we are done. Thanks again for coming to this discussion section, and see you next week.